and then look at these are some simple functions of two random variables which are easy to discuss. That is what we are discussing. Then we will go ahead and discuss functions of a single random variable, generate case, and so on. Let's say x is uniform 0, 1, y is also uniform 0, 1. Then let's look at a function where another random variable z, which is a minimum of x comma y. Okay. So how do we arrive at this? To do that one, what we will look at first, we are looking at the PDF or the CDF of z. Let's take the CDF of z. It's many times it becomes easy to come up with a condition governing the CDF of z rather than starting out with the PDF. So what it means is z is such that z has to be a minimum of x comma y. That's what we are looking at. That is probability that z is less than or equal to some z is what we are looking at. That is probability that minimum of x comma y has to be less than or equal to z. This is the capital Z. So the minimum of x and y, okay, has to be less than or equal to z. What does that mean? X should also be less than z, y should also be less than z. Okay, because their minimum is less than z, so x should also be less than z. Assume, let's take a case, x and y are independent random variables. Then this factorizes into their individual terms. Because you can find out actually, even if you use the joint PDF, we have not told what the joint PDF would be. Okay. Of course, it's actually x and y are uniform this one. We have told just like that. If it is, they can also be in general need not be independent. Now, if we take a case where they are independent but individually uniform, then what is this one? This is fx at z into fy at z. So how is it defined? How is the fx or this one? Because they are uniform between 0 and 1. This is what is fx of x would be same as fy of y will also be like this one. Whereas if you look at this is how it will be. Okay. So in general, if A and B, if it is uniform between A and B, if fx of x is uniform between A and B, it is 1 over b minus A. I will write it, of course. To recall, then fx of x is 1 over b minus A for x lying between A and B and 0 otherwise, and fx of x, if you look at, it is 0 up to A and then it will become after B, that's known. So in between, how it will be? We have to integrate it at till any given x here. So that will be given by, if you want, and with x minus a by b minus a for x lying between 0 and this one. It will of course be 0 in these places, 1 in these places. This is the general one. So in this case 0, 1, 1, a is 0, b is 1. So it is just x by 1, it is x. So what we have is z into z, that is equal to z square. That is what of z of z. So if you plot it will be 0 to 1. Of course, below 0 it will be 0 only. Minimum of no value of z, okay? Minimum of x and y are confined between 0 and 1. Then minimum of 1, okay, cannot take any value below this one. Okay? So this is 0, and after 1, definitely minimum of x and 1 will be less than 1. So after that it is 1, and up to that it is square function. It will go like this. And fx of x, fx of z is what we need. But from CDF we have to get the PDF. Okay. We will do that. That's what we are going to do. So this is what we have to do. We have to differentiate it with respect to z. Okay. So this is valid. Actually, what we are doing is, this is fx. Fx is a function, but it is a function of z. The functional form is it's a density function of x. But if we are evaluating it, z of z, okay, which is z squared. So it will be just to 2z. Okay, so fz of z is equal to d by dz of fz of z. That is what we are doing. So we get z squared differentiating with respect to z is 2z. So this is the density function of z. And how will that be? It has to be 2z and it has to be normalized also. So at 0 it is 0, at 1 it is 2. And it has to be like this. And after that it is 0. See, this is a density function, not a CDF. So it is only confined here. It is 0 in this place, it is 0 in this place. But between 0 and 1, it takes a form of 2z. So just substitute a line. So at 0 it is 0, at 1 it is 2. So and height is 2 at this point. But it is valid, it is a valid PDF. PDF can become more than 1 also, but the integral over any range has to be, it's a probability which has to be less than 1. So is this valid? For example, this is 1, this is 2. Area is half into 2 into 1, that is equal to 1. So the area is 1. So this is a valid density function. So what? So we have looked at this function, we have derived this density as well as the CDF of the minimum of x and y for the case that they are both uniform and independent. Any question?
How did we get that, that P of x s equals z into P of y s equals, I guess that would be z, but yeah, how did we come to that? So I mean, shouldn't it be or condition instead of the and condition? I mean, if x is s equals z, and even if y is greater than z, the minimum is still going to be less than z, right? So why is it an and condition?
So one minute. Let me just check that one. Are we deriving minimum or maximum? I just said maximum means this condition was getting obeyed. Okay, max of x comma y means x r should also be less than z, y also should be less than z. Is that right? I will clarify it. Then we will so then later let's look at this one. Okay. We will do it for exponential, then it will become, let's see what x and y are exponential, independent, with parameters lambda 1 and lambda 2. Then let us define z, which is minimum of x comma y. Okay. Let's take the case where z is greater than small z. This is the CCDF. Okay, yeah, this is the CCD. And this way of approach is the one. So, what it means? Property of minimum of x comma y is greater than z. So, what does that mean? Minimum of x and y has to be greater than z. X should also be greater than z, y should also be greater than z. And if x and y are independent, and what is this one? This is the CCDF of x, CCDF of y. So because they are exponential, what are their CCDF? E power of minus lambda 1 z. Why? Because, so you can see that x is independent. So fx of x is 1 minus e power of minus lambda 1 x. And CCDF, any x is same holds good for y also. CCDF always have this form. So that is what we are using, but we are computing at z. E power minus lambda 1 z and e power minus lambda 2 z. That is equal to e power minus lambda 1 plus lambda 2 into z. This is probability that z greater than z. So what does it tell you? Z is a random variable that whose CCDF has this form. This form is the same form of a CCDF for an exponential random variable. Only thing is the parameter becomes lambda 1 plus lambda 2. See, if the CCDF is a unique signature of any random variable, if two random variables have the same CCDF form, they have the same random variable. Other things, PDF, everything else will be the same. So Z is also exponential. And what will be the parameter? Whatever that occurs here. So it is also exponential, but its parameter is lambda 1 plus lambda 2. So if you have two exponential random variables of parameter lambda 1 and lambda 2, their minimum is also exponential with parameter lambda 1 plus lambda 2. They just add up. What it means is, suppose we have got two equipments, components that you are going to put into use, or a light bulbs, let us say two light bulbs are going to put into use, and each one's lifetime is exponentially distributed with parameter lambda, same lambda or different lambda, lambda 1, lambda 2. Then you are looking at the fact that the whole, so let us say you have an aircraft or you have two engines, not a good example of the aircraft with two engines. Even if one of the engine fails, the aircraft fails. Then you are looking at the lifetime of the aircraft. Okay, so it is the minimum of the lifetime of the two engines. Then it will be the parameters will be the sum of these two, which means that it is likely to fail earlier. You can see how it will be. Why? The expected lifetime. Let's look at that one. E of x is equal to 1 over lambda 1. Okay? And E of y is equal to 1 over lambda 2. In the case lambda 1 is same, it is 1 over lambda. And E of z is equal to 1 over lambda 1 plus lambda 2. If it were the same, then both these things are 1 over lambda. And for this one it is 1 over 2 lambda. Okay, so the expected lifetime is smaller because we are looking at the minimum of it. Then you want to say that what is the probability that x is less than 1? That is something you can ask. I have two components, okay, or two people, let us say they do the job, there are two servers serving some customers in this one, their rate or exponential, the service time is exponentially distributed with parameter lambda 1 and lambda 2. You would like to know that who will complete the service earlier, whether x will complete the service earlier than y or so, or the component x will it fail before y fails and so on. So that those are the questions. So how do we find it? For that you use the condition. See, just like that, if you compare two random variables, you won't know what to do. But if you do a condition, then it becomes easy. Probability that x is less than y, but if I am given a value for y, then it is easy to find. Y is equal to x. If I am given like this one, then it is easy, because then it actually becomes the random variable x is less than this y, which is nothing but the CDF of x. Okay, that becomes easy to find. So that way you can put. But this is a condition. You arrive at only under a condition you are doing. But in general, y can take any value over its entire range, 0 to infinity, with the respective probability. So to uncondition it, what you have to do is, you have to multiply it by the corresponding probability and then integrate it over the overrange, full range. That is how we have to do. This is the conditional probability. It is conditional CDF. So this is a conditional CDF of x given y is equal to y. To uncondition, you have to multiply it by the density function of y and integrating over the entire range of y, then y will not be over, but this condition will, every time the condition holds good and all possible y value are being taken into account, so you will get this unconditional probability. So Of course, y will take only value from 0 to infinity. We can put dy. So what is this one? This is nothing but again, if you want, I can write. So y is taking this value and you are asking this one. Given this condition, random variable takes only a particular value. So that can be put here. What is this one? This is fx into fy. Look, this is the CDF of x evaluated at the value y. This is the density function of y. Okay, evaluated at y into dy. So what is this CDF of x? It has the form 1 minus e power of minus lambda 1. That is the form. And you have to solve wherever you want to find, you have to substitute that value. Right. And what is the PDF of y? Exponential PDF. Lambda e power of minus lambda something. Wherever you want to evaluate, you have to put in that place. So, but y has the rate lambda 2. Okay. In the case of x, you have put lambda 1. For the case of y, you have to put lambda 2. So it is lambda 2 e power of minus lambda 2 into, you are evaluating at y, into dy. So you will get lambda 2 e power of minus lambda 2 by dy minus e power of minus these two factors. Of course, lambda 2 is here, you will take it out. These two factors, it is e power of minus lambda 1 plus lambda 2 into y into dy. Yeah? What is this quantity? Integrate it and tell me, otherwise just tell me 1. Because you are integrating over the entire minus lambda 2 into this is you can see that it is 1. This one, if I put infinity, it becomes 0. If I put 0, it becomes 1. Yeah. So see, there will be 3 minuses, okay? Minus lambda 1 plus lambda 2. I will put it retaining. So there will be 3 minuses. This minus 1 cancels, but this one again leads to this one. This will 1 minus lambda 2 by lambda 1 plus lambda 2. That is equal to what? Lambda 1 plus lambda 1 plus lambda 2. This is the probability that x is less than 1. That is, probability that x will fail before y is just given by this form of a ratio between the rate of y's lifetime distribution parameter divided by the combined one. Similarly, you can also find probability that y is less in an equal manner. It will be lambda 2 divided by lambda 1 plus lambda 2. Why this form comes? Because what is lambda? It is the failure rate. See, 1 over lambda is the lifetime. If the rate at which it fails is larger, its lifetime is smaller. Clear? So, if lambda 1 is more than lambda 2, the lifetime, it's like this. That is x component, this is x, this is y. X is not a good component, its failure rate is larger than the failure rate of y. Therefore, the expected lifetime of x is smaller than the expected lifetime of y. Now, what does this do? Probability that x will fail before y, it's very likely because x is not a good component. So, that is given by lambda 1 by lambda 1 plus lambda 2. Lambda 1 is larger than lambda 2. So, this would be more than, it will be larger as compared to lambda 2 by lambda 1 plus lambda 2. And their sum should be equal to 1. If I ask probability that x is less than y plus probability that y is less than x has to be equal to 1, because one of these conditions should hold good. And it goes good. Lambda 1 plus lambda 1 plus lambda 2 plus lambda 2 by this one, it adds up to 1. Okay? So, does this ring when you are paying bills? Did you encounter this situation before in quiz? Okay, the same as the customer, which customer completes before other customer? Okay. But it just you don't, it's only the conditional density function you have to use. Then let's say you have got x, y. Let's look at the case of random variable z, which is f or become x plus y. Minimum we have seen, maximum also can be minimum, maximum in a similar manner we can do. We have looked at the sum of two random variables, a function of sum of two random variables. Okay, some general things can be told for x and z. Let's take the case when x is discrete, okay, and y, that is its die, let us say 1 to 6. This is also 1 to 6. Okay, we looked at this kind of a problem. Z is equal to x plus y. You throw two die at random, both have fair dice. Probability of getting any one of the 1 by 6, 1 by 6, and then your z is the sum of them, and it should of course lie between 2 to 12, and then you are asking what is the this is a PM, discrete random variable, what is the probability found from them that z is take the value 7. Then how do you find it? What are all the different cases that lead to z, the sum being 7? You look at case like 4, 3, 3, 4, 5, 1, 1, 5, and so on. So, what in general we are doing is equal to sigma, okay, x can take a value from 1 to 6. Probability that x is equal to, this I from 1 to 6. Probability that x equal to I takes one of the values 1 to 6. And if that being the case, what is the value of y that are allowed? In order to maintain the condition z is equal to x plus y, you have to sum it over the entire PGF, bidimensional PDF, the PGF of x and y. But only the condition is, this condition has to obey. With this restriction, you do it. And they are independent, that is why I am right now factorizing it. So x can take any value y, but to obey this condition, y should take the value z minus I. Small z minus I. So that is what this is actually, that given value small z. So, looking at it. This is where it will come that whichever valid values will come. If you put then 1, okay, 1 is allowed, then it becomes 5. Okay, 3 becomes 4, 4 becomes 3, and so on. So this is how you can get it. This is how you can arrive at it. And have you encountered this kind of a summation? Yeah, it's discrete convolution. In a similar manner, you can have it for the continuous case also. So you have got fx of x, fy of y, the density functions being given, then z is x plus y. You are asking, okay, we'll write it maybe separately. You want a z of z. That is what we are doing. This is what we are looking at. So over the entire domain of the PDF of xy, you have to integrate it, but the integral should be such that this condition is obeyed. This is this condition. This z. Z, because you are evaluating at z. Okay? So x plus y together should add up to x. That condition if you enforce, you will get a subset in the whole in this one. There you have to integrate it. So, to do that one, x and y are now right now general. You take one variable as a free variable which can go over the entire value, and other is being confined. So x goes over the entire valid domain, and this one has to be confined from minus infinity to z minus x. That is what y. So that and fxy of no, this is the this is this one. This is this it's not function. This is for f z of z. Because we are integrating the density function. Okay, in the x and y, then you will get the cumulative density function of z. So this is how you can get it. When it comes to fz of z, it is a single one. We'll see. Okay. Yeah. Again, this will be correct okay. Because this is functions only. It's only the integral is only a small x. Z is of course a given constant at which you are computing the again this is the discrete convolution integral. So now let us look at some functions of random variable. Again we already looked at for the case of uniform that is a linear function. We are looking at, so x is a random variable, there is a function g of x being given, so you can define a random variable y which is g of x. Given the density function CDF of x, how do you find the corresponding density